Okay. All right, let's get started. So I want to finish something from last lecture, which we didn't get time for. So most of the last lecture was about proving that technique for proving that a particular language is not regular, right? So how did we do that? We developed this what's called the fooling set technique, right? So recall that a regular language should be recognizable by a DFA, right? So, but what is a DFA? DFA is nothing but a program which has fixed memory, right? It has a fixed memory. It cannot store anything other than what this finite memory is, right? So that clearly is a strong limitation in programming, right? If you can't store information, then the program is very limited. So how do we develop this fooling set technique to say that, okay, if a language requires us to somehow intuitively memorize larger and larger amounts of information, then it cannot be regular, right? So one way of proving that formula is to say, if we can, any machine with finite memory can be fooled if the language is sufficiently rich, right? So that's the technique we developed for proving that a certain language is not regular, right? And it's a complete technique in the sense that you can always prove using that technique. So there's one, like with many things in algorithm design and other problems in computer science, there is this very powerful notion of a reduction, okay, which we'll see again and again, and it's both useful for proving things about developing. Can we please calm down, please? Okay. So this notion of reduction is very important. So what it allows us to do is build on existing results to prove new results without starting from scratch. Okay. So we'll see many instances of this, right? If you already have an algorithm for some problem, you don't want to, a minor tweak to the problem, you don't want to rediscover a new algorithm, right? And that idea we'll see in this context as well. And the idea is the following: suppose I already showed that a particular language is not regular, right? We used a fooling set construction or some other construction, and somebody showed us that this language is not regular, right? Now what we would like to do is to say, can I use some simple ideas, high-level ideas, and be able to prove that some other languages which we encounter are also not regular, right? That is the idea of building on existing results to prove new results, right? So let's see a very simple example, and you'll see the power of this method, right? So recall here is a language which we already saw, but let's look at it again. So L is a set of all bit strings which have equal number of zeros and ones, okay? Equal number of zeros and ones, all right? Now we also saw this is a language which is L prime, which is 0 to the k, 1 to the k, k greater than or equal to 0. So what is the relationship between these two languages? Yeah? L prime is a subset of L, right? But it's a more restricted language, right? It has more structure than this, right? So we showed, the very first example we showed that of a language that was not regular is the L prime, right? Okay? Now we want to say, now we already know that this is not regular, and now I want to prove that this language is also not regular. Okay, we actually saw a fooling set for this, right? But maybe we don't even know, we don't remember the fooling set argument, right? Or we've forgotten, and suddenly we are in the middle of an exam and like, what is the fooling set? I'm fooling myself, right? Okay. So you say, okay, can I prove it a different way without remembering all that? Okay. And here is a very simple proof. If you knew that this was regular, and you can say, Chandra proved it in lecture, I can use it according to the course policies. So can I do something simple? So okay, so how do we do this? Here is a simple observation, right? I want to claim that L prime is nothing but L intersection a regular language. Okay, so how can I get L prime? I claim that remember L prime is a subset of L, right? Okay, but how do we get L prime? I claim take all the strings in L, I mean that's a language, right? And you intersect it with the following language. What is the language? 0 star 1 star. What is 0 star 1 star? All strings which are all zeros before all ones, right? Any string of the form a number of zeros followed by a number of ones. That's clearly a regular language. Why? Because I'm giving a regular expression for it, right? Okay, I claim that L prime is L intersection L 0 star 1 star. Yeah? If you have equal number of zeros and ones and the string looks like zeros followed by ones, how does it look like? It must be 0 to the k, 1 to the k for some k, right? And conversely, right? Any string in this is in L prime, right? So equal, right? Now I claim we are done, right? Why? I want to claim because we know L prime is not regular, we can conclude L is not regular. Why is that? Proof by contradiction. Suppose L were regular, okay? Suppose L were regular, then because this language is regular, the intersection also should be regular, right? But that would imply that L prime is regular, right? But we know L prime is not regular. So what went wrong? It must mean that L is not regular. Okay? That's simple technique, no? This is, in general, this is called a reduction. What we have done is that we have used, in fact, I don't even need to know the proof of the fact that L prime is not regular, right? That's what I mean, right? You just have to know that fact. Somebody told us that L prime is not regular. We don't even have to remember the proof, right? How did we prove it? We don't care, right? If somebody said, we know that theorem, that's it. We can use this simple observation to show that L itself is not regular. Okay? So this is a technique using, so why, I mean, in fact, you can do it with many other closure properties, right? What do we want to, I mean, here is a general technique. I want to know whether L, I have a new language, L question mark, and I don't know whether it's regular or not regular, right? I want to know, is it regular, is it not regular? Right? Maybe I suspect it is not regular. One way to prove it is, let's go down to fooling sets, understand the language really well and try to go from scratch. The other way is to say, okay, let's see if we can start with some known regular languages, right? We know a bunch of known regular languages, simple regular languages, and apply some closure properties and get a new language which we already know is not regular. Okay? If we can do that, then clearly this cannot be regular, right? Why? Because if this was regular and all these closure properties are going to preserve regularity, and if you end up with a non-regular language, that must mean that this must be non-regular. Okay? Okay, what does it require us to know? It requires us to know simple regular languages, and it requires us to know some simple non-regular languages also, right? Like 0 to the k, 1 to the k. That's something standard we have already seen, right? Once we have a bag of things that we know, we can tackle new problems without really going through the nitty-gritty of the proof. Okay? So this is another proof technique, and we'll see it again in algorithm design. Lower bounds, reductions are going to be very important in all of computer science in general, right? We don't want to, it's like subroutines, right? Somebody has a library, why should we rewrite the library, right? Doesn't make sense, right? So this idea is not only practically useful, but is also a very fundamental theoretical technique. Okay? So that's all I want to say about regularity, right? Non-regularity. That means either you can use a fooling set argument, or you can use this argument where you can use existing results and closure properties to prove new results. Okay? Those are the two main techniques to prove that a language is not regular. Okay? Okay. All right. So now we are going to today's lecture, which is on a new topic, which is context-free languages and grammars. Okay? So what are these? Okay? So, most of you, I don't think most of you have taken 421, but you will see this material again in 421. It's because it's important in programming languages. So why did we study regular languages, right? Regular languages are a very simple class of languages. Yeah? We saw two aspects of regular languages, right? Regular languages are the same as the ones recognized by simple programs, right, DFAs. So there is this nice dichotomy or a relationship between expressivity of a language and computational parts of the language, right? So why? I mean, remember, we are already started using regular languages in our vocabulary, right? So suppose you want to now think about a language, you say, I know regular expressions. It's a compact mathematical way of precisely stating what I have in my mind, right? Once you know regular expressions, you can say, okay, for a restricted class of languages, I have a vocabulary now, right? You don't have to say L is a set of all bit strings which have zeros come before all ones. That's kind of clunky, right? You can say 0 star 1 star, right? Now suddenly you have a nice expressive way to express a class of languages, okay? But because the languages are simple, we have very simple machines, DFAs, which help us recognize it, right? But then we also saw that regular languages and regular expressions are not so powerful. For example, what do we do in programming languages, right? So let's say you're writing C or Java or any code you have written so far. They are too rich for regular languages, right? What is the first thing we learn in programming other than print hello world, right? We learn how to do addition, multiplication, and expressions, right? So, I mean, you have to be able to say in a programming language something like, x equals to 3 plus y plus, z plus, something like that, right? You want expressions, right? Something like that, right? Z star y, right? So this is a simple expression you will see in programming languages. But we saw that, in your lab, you saw that regular languages are not rich enough to even capture things like this, because you have to be able to check whether the parentheses are balanced or not, right? So clearly your programming language is not going to be expressible as a regular language. So we want a richer language, right? A better way or more richer way to express what we want. Like, for example, a programming language is a more restricted way of, a more general way of expressing what we want. Well, with more power comes also the issue of how does the compiler know that your C program is actually a C program? What does it mean that it's a C program? Okay, that is, you write something, right? The compiler is actually checking, right? It's doing something. What is it doing? Right? What do you think your compiler is doing when you give it to the compiler? It has to first check it is syntactically correct, right? Okay, what is the meaning of it is syntactically correct? Do you know what the meaning of program being syntactically correct? Yeah? Yeah, it follows some rules of the language, right? What are the rules? Where are the rules? Have you seen the rules? How did you learn to program in C? Or Java or whatever language, right? The question is, are there rules? Is the question. Yeah. Okay, and how did you figure that out? Compiler error, right? So we are actually doing trial and error, more or less, right? And pattern matching, right? But the compiler cannot do trial and error, right? It must have some rule book, right? Which says, and it has to be automated, right? It can't be, oh, today I feel like accepting your program, right? Tomorrow it's not okay, right? Or like, I like his program, but I don't like her program, right? What is it doing, right? It has to have a rule book, right? And what is that rule book? Okay, so there is a rule book, and that rule book is not obvious to you till you take 421, but it looks like this, okay? It's a whole bunch of rules of what is allowed, okay? Okay, but what is the language for these rules, right? There is why Java is a little different from C, if it's different from Python. How do we specify rules of a programming language, and what is the class of languages that it belongs to, right? Well, two things are important for any class of languages. One is that it should be a good language to allow us rich expressibility. The second thing is we also need efficient algorithms, right? In the sense that, if this compiler cannot check whether it is a valid C program efficiently, what's the point of being very expressive, right? So both are important, right? We haven't stressed that efficiency yet, but, we are going to work with expressivity. So there is this class of languages called context-free languages, and they're very powerful, and for computer scientists, the clear motivation is programming languages, okay? In addition to many other applications. But there are many other applications of context-free languages, and if you want to express English, right? What is English? Is there a grammar, right? What is the class of, do natural languages have some rules? What are they, right? If there are. Now, why is it important to understand? It's a very fundamental philosophical question, of course, but it also has many applications, right? As you know, many of the tasks in natural language processing are automated, what are they doing in the back of the thing, right? So they have models of languages, right? And it's not quite, they're very rich. Natural languages are very rich. So, but people study the class of languages, which, how do we model natural languages and stuff. And then, you can use grammars for things like, producing this kind of figures and producing these kind of figures, right? Some of you from India may recognize this kind of things, right? These look like intricate patterns that people draw on ground and stuff, right? But you can generate them automatically, right? And how, right? You can do all this stuff if you have some class of grammars and languages that allow you to generate this. Okay, so we're going to study this class of nice languages called context-free languages today. Okay, so what is a context-free language? I'll go in a formal system, right? So it is given by, hopefully we are now used to some formalism so that I don't have to give a long example and then do the formalism, then again give a long example, right? So we are getting a little better at that. So a context-free grammar has 4 parts, okay? The first part is the V, is historical notation. Why is it not sigma? We'll see, it's just historical notation. V is a finite set of non-terminal symbols, okay? I'll give you an example soon. Okay, T is a finite set of terminal symbols. You should think of this as the alphabet, okay? Like in DFS, you should think of this alphabet, but see, we're not calling it sigma. Why? I'm sorry, just historical reasons, right? And then P is a finite set of productions or rules. Okay, we'll see what these rules look like. And they look like this, like the following form. They'll have one non-terminal with an arrow and saying some string of terminals and non-terminals together. Okay, I'll show you an example. Okay, and finally, S is simply a start symbol. It's a specific non-terminal symbol. Okay, it is a part of the non-terminal. So let's see an example. Right, here is a grammar. There's only one non-terminal, S. Right, remember it has to have at least one non-terminal, the start symbol. Okay, it's S. Okay, and there are 2 terminals. The alphabet is A and B. Okay, yeah. And what are the rules or the production rules? S goes to epsilon, or it can go to A, or it can go to B, or it can go to ASA or BSB. So this is a compact way of writing. The rules are the following rules. S goes to epsilon, S goes to A, S goes to B, S goes to ASA, or S goes to BSB. So they're all possible rules, right? It's just that, this bar notation is OR, right? It just is a compact representation of, instead of writing all this, you can just write this. Okay? Is it clear? Okay, now we have to understand what is this meaning of this, what is the language generated by this, whatever rules or grammar or whatever, right? So let's understand this. Okay, so the idea is very simple. You start with the start symbol S, and you can apply a rule, right? What kind of rule did we apply? We know that, S goes to ASA, right? So this is one of the rules allowed, right? Okay, so we can replace S with ASA. Now you say, okay, look, this has sorry, this should be, that is a small a, okay? Okay, so now this S can again be replaced because it's a non-terminal which generates things. We can replace this with BSB, okay? And we can replace it again if you want this S with BSB. So we get bigger and bigger strings, no? Yeah? That's the rule, right? You start with start symbol. You can use a rule to get a new string. And then inside that string, if there is a non-terminal, you can use another rule to expand it further, right? And you keep going. And eventually what happens, you can decide, okay, I'm tired of this, so this should be B. I'm sorry, there's some typos. Eventually, S can go to a terminal, you get A, B, 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 A, right? Okay. So we say that, remember, this has only terminals, right? It doesn't have any non-terminals, yeah? So we say that this string is derived from S, right? That's okay. So now we want to understand what are all the strings that can be generated this way from S. Just guess, what do you think is the strings that this thing can generate? What else can it generate? Yeah, okay, good. So anybody else who didn't hear him? Yeah. some others from there. It's a big room. So what other string can you generate? Can you generate A? Yes, right? Because it's a single rule. You can generate B, you can generate epsilon. Can you generate AA? Sorry? Yes, right? Because I can generate A as A and S can go to epsilon. Yeah? You can generate AA, you can generate BB. Can you generate ABA? How? A as A and S can go to B, right? Yeah? Okay. So I claim that you can generate all palindromes with this. Yeah? No, there's no transition here, right? These are the rules of the game. The rules of the game are you start with S and you can apply a rule that we have. What are the rules? These are the rules that allow you to replace S with any of those rules can be applied. Your choice. Okay? Yeah? It's like recursion, right? It's just a recursive way. Okay. Okay, I claim that this grammar generates precisely the set of all palindromes over AB. Okay? Right? Sort of makes sense, yeah? Okay. Okay. Okay, I claim it's the palindromes. Lenny had this nice nice palindromes. I didn't know this, right? It's all palindromes. If you remove the punctuation, okay. It's hard to see that they're palindromes, but they're funky, okay. So you can go and waste your time on this website if you're interested on palindromes, right? Okay, here is a quick question. Give me a 5-letter palindrome. Just for fun, right? Somebody asked my kid, so I'm asking you, right? Give me a 5-letter palindrome. No, it's interesting, not like A, come on. English word which is a palindrome. Ah, good, yeah. Okay, kayak, right? Okay, all right, this is fun. Okay, let's get back to math, right? Okay, let's see this language. We know this is not regular. Now let's try to write a grammar which would generate this with knowing the very simple rules. Let's see how we can write a grammar to generate. It's one symbol. Let's see. Okay, so we have only, I'm saying this is very simple, right? I have S, right? Only one symbol. I'm claiming that it's a very simple language, so we can generate this language. What should we have? What rule should we have? Recursively, we want to think about it, right? I claim, just like palindromes, we can do this, right? Okay, 0 goes to, S goes to 0 S1, right? And epsilon, okay? Okay. I claim these rules are enough to generate this language and they only generate that language, right? Yeah? Is that sort of clear? Yeah? Okay, so that's it, right? The thing is, the interesting thing is that this gets more powerful when you have many symbols, right? Not just one symbol. We have been playing around with one symbol, 2 rules, right? 3 rules. But you can have 1,000 symbols, right? Gazillion rules, so it can generate complicated mutual induction and stuff. So we'll see more examples, right? So some notation, right? Because there's so many symbols floating around, we have to be a little careful. So there is just some convention. This is not absolute. Typically, we'll use A, B, C, D for terminals, right? Alphabet 0, 1, right? Small letters, right? And capital letters A, B, C, D, and so on for non-terminals. We saw capital S is a non-terminal, right? But then we'll use U, V, W, X, Y, and so on for strings over the alphabet or the terminals, okay? But we'll be interested and we need to understand also strings which have both alphabet and non-terminals, right? Because they'll come about in the middle of the thing, right? A as A came about, right? That's a string over both the terminals and non-terminals, right? So we'll use alpha, beta, gamma, and so on. Okay, this is just vaguely, right? So these are for strings in V union T star. That means we combine both the terminals and non-terminals, right? Okay, and we'll use X, Y. That should be Z. For if you don't know whether it's a symbol or a terminal or a non-terminal. Okay, okay. Now we have to do some. We need to make sure we have language to reason about. What does it mean that this S generates a string? What is this, right? Let's make it formal, right? So we have a grammar. Now how do we formally state that, S can derive this string, right? Because it can take many steps to derive something. So we have to do one step at a time. We understand it intuitively, but let's formalize it. We say that, you take some string, right? Take a string like this, right? 0s1. What is this string? This string is in what? This is in V union T star, right? It's a string which contains both terminals and non-terminals. Okay? We say such a string derives another string in one step. That's the derives notation via this grammar. What happens? The second string alpha 2 is obtained by the first string by replacing one non-terminal, right, with a rule, right? Okay? We take a string of symbols and say, how did we generate something? We looked at a non-terminal and we expanded it using a rule, right? Okay, here is an example. So why do we say 0s1 generates 00s11? Because we took this s and applied a rule to replace it with 0s1, right? Yeah? One step. We are allowing one step, right? Okay? Yeah. That's the notation, right? It means that alpha 1 derives alpha 2. This is a formal mathematical definition. So this is a notation. When we say this, it means that this string can be obtained by this string by applying one rule of the grammar. Okay, one rule of the grammar, right? So this is the math. Let's first understand the example, right? Why does S derive epsilon? Well, because that's a rule, right? There is a rule in our grammar, right? Remember, this is the grammar which is generating 0, 1 to the k. We have to have a grammar in mind. Okay. So why does S derive this 0s1? Because this is a simple rule, right? But I'm saying this applies to bigger strings too. So 0s1 is a string, right, of both terminals and non-terminals. And the definition says that this derives this because I replaced S with 0s1, and that is allowed because it's a rule in my grammar. Okay? Okay? When we have to do formal proofs, we need to know precisely what exactly are you talking about, right? We can't just hand wave, right? So this is why we need that. Okay? Yeah? Make sense? Yeah? Okay. Okay. So then once we have this, we can talk about, this string can derive that string in many steps, which is the obvious thing that you can derive one step at a time, right? Yeah? When do we say that alpha 1 derives some string in k steps? Well, you just inductively define it, right? You do one step, then you do the next step, and so on. How do we say? We don't say and so on, right? We define it inductively, right? We say that, alpha 1 derives alpha 2 in 0 steps if the same string, right? Okay? And alpha 1 derives alpha 2 in k steps if you can go from alpha 1 to beta 1 in one step, and then from beta 1 to alpha 2 in k minus 1 step. Yeah? Not hard, but this is important to formalize. And then, alternative definition is that with strings always we go from the left to the right, right? Sometimes you want to go from the right to the left, right? You want to do the last thing. You can also say that alpha 1 derives alpha 2 in k steps if alpha 1 derives beta 1 in k minus 1 steps and beta 1 derives alpha 2 in one step. So that we're going to the end of the string, right? And the last step of the derivation, right? They're the same thing. Okay, I have to formally prove that, but it's fairly obvious. Okay, and then we can define the star. What is a star? That is alpha. The derived star, right, is like alpha 1 derives alpha 2 in as many steps as you want if there exists some k such that alpha 1 derives alpha 2 in k steps. Okay? Okay? This is a shorthand for the closure, or what's called the transitive and reflexive closure of this relation. Okay? It's intuitive, I'm just putting mathematical words. We say S derives epsilon, right? This star means that, we are not paying attention to the number of steps, right? Precisely, right? Okay? So 0s1 derives this string, right? Yeah? Because you can keep on doing many steps and then get this string. Yeah? According to the grammar. You agree? So far so good? Yeah? Okay. And then once we have this notion, then what is the language generated by the grammar? It's what we have intuitively seen, that all the strings that are terminals in T star, which can be derived from the start symbol. Okay? anything that can be derived from the start symbol is any string in T star that can be derived from the strong start symbol is a part of the language, and only those are part of the language. Does that make sense? Anything that we can get from the start. Questions? Okay. So and language is context free if there is a grammar which generates that language. Right? Now you may ask, what is this meaning of context free? Why did people call it context free? Yeah. Sorry? T star, yeah, exactly. Yeah. See, we are using regular expressions now, right? T star is, we know what T star is, right? It is a set of all strings created from T, right? So it's like that's like sigma star. We just let all strings in T star that can be generated from S. Yeah. Okay. So why is this called context free, right? You may wonder, who gave this name context free, and is there a context for it, right? Okay, remember the rules of the context-free language, right? What can the rules look like? Yeah?
Yeah, no, I just got a question regarding the symbols in
Yeah.
Instagram. So B is the non-terminal symbol,
Yeah.
T is the terminal symbol, and what are P and S?
Productions, the rules, and S is the start symbol.
Okay.
Yeah. Okay? So why is it called context-free? Because the rules are all of the form A goes to some non-terminal goes to some string, right? You can apply that rule anytime you want, right? Okay, there is no constraint on your applying. But what is context sensitive, right? There is a class of languages called context sensitive, and that's why these are called context free, right? A context sensitive language has rules of the following form, which are more general. They say that okay, alpha A beta goes to some gamma, right? Why is this rule more complicated? This rule is more complicated because it is saying you can expand A to something only if you're surrounded by alpha and beta. Okay? In the context of alpha and beta, you can expand A, otherwise you cannot expand. So this is called context sensitive because I'm not giving you freedom to expand A whenever you want. Right? Only when you're surrounded by some other information, right? Okay, that's called context sensitive, but that's a much more complicated class of languages. If you allow rules like this, you can generate some very crazy languages, okay? Crazy in the sense that very complicated, right? Context free doesn't allow you the freedom to specify on the left hand side of the rules anything complicated. You can only put one non-terminal, right? So it's a little bit limited class of languages. That's the name, that's why they're called context free, right? You're not allowed context, and you can apply it whenever you want, right? The more freedom means that it's less rich. Okay. So if a language is context free, if there's a grammar for it. Okay. Let's do this two languages for practice. So we already saw this very simple grammar for 0 to the n, 1 to the n, n greater than or equal to 0. Design a context free grammar for this language, which is 0 to the n, 1 to the m, where m is greater than n. Okay, what does it mean? I want the number of ones to be bigger than the number of zeros. Go forth and produce a grammar. Yeah. You can do whatever you want, but I want you to write it and figure it out. Oh yeah. You can add more symbols. Yes. Yeah. You decide how many symbols you want. Right? You can add more non-terminal symbols and stuff. Right? Try this. Okay. Yeah. Question. Is the language clear? Yeah. This is also not regular, right? We saw that it's not regular. How do we generate this language? Remember, this is very simple, right? How do we generate this slightly more complicated language? Yeah. I want you to work on it, not like raise your hand. Okay, if you already see it, great, but I want you to write the grammar down, right? For yourself and talk to your neighbor and see if it makes sense or it is, right? Right? I mean, if we know the definition, we tried, we had some familiarity with the grammar. feel free to add more symbols, right? You know. Yeah. No. I mean, that is just to remind you of the other grammar. You can do whatever you, right? Oh. Oh, I didn't put. Okay, how are we doing? Anybody needs a hint? How do strings in this language differ from 0 to 1? I mean, what do we need to do? Think of it as a subroutine, right? If I already know how to generate the language, the 0 to the n, 1 to the n, what should I add to the strings at the end? A non-zero number of ones, no? If I can tack on, that's a very simple language, you know? Suppose I want to ask you to generate all strings which are just 1 star. How do you generate? What is the grammar for generating 1 star? I want to generate 1 star, right? Using context-free grammar. How will you do it? Or 1 plus, yeah? 1 plus, say. Okay, 1 star is fine too. If you want 1 plus, you don't want epsilon, right? Yeah. So once you have those two pieces, we know how to do 1 plus, right? And we know how to do 0 to the n, 1 to the n where they're equal. Then what does a string in this language look like, in the new language? It's a concatenation of this language with 1 plus, no? Our new language is simply the concatenation of the old language with 1 plus. Yeah? Okay. So we know how to do 1 plus, so we remember we can use more symbols, right? So for this we can say, okay, I will create a language which is 0, a 1 or epsilon. What does this do? What does a generate? Because I just change the name from S to A, right? Okay. Now let's see, B generates B1 or 1. What does this generate? 1 plus, right? Okay, now I want S goes to what? AB. Okay. All right? It's a modular way of designing the language, right? Of the grammar. Yeah? Is that good or not good? Yeah? Yes, so what did we do? We just, this is, we already understand this. This is 1 plus, right? B generates 1 plus. And we're saying S can go to A, B. What does that mean? Well, we just, this guy will going to generate a string and this guy is going to generate a string and we concatenate it. Right? Yeah? Questions on whether this makes sense or not? If it doesn't, we should understand that something about the derivation is not clear to us. Yeah. No, so, yeah, I mean, the thing is, let's see how it can generate 0, 1, 1, right? Okay? What happens is, S generates AB, right? I mean, we have to put this squiggly arrow, which I will. Okay, then what can A generate? A will generate, 0, A1. Now we keep B, and then this will go to 0, 1, B, because, I can use A goes to epsilon, right? And now this will go to, 0, 1, 1, right? Because B can go to 1, right? Okay? So think of non-terminals as recursive programs, right? So each non-terminal is a code, right? Right? Think of it as a program which we can. What are the rules, right? The rules are like the cases of what all things it can call recursively, right? It can either go to a base case if it is all terminals, or it can go to what? It can call other functions, right? What are the other functions? Whenever the production rule is there, if AB is a production rule, it can use that, right? It means it calls A, it calls B, A will return some string, B will return some string, and it will concatenate it and spit it out, right? That's what it is, right? Each non-terminal you can think of as a recursive. They're mutually calling each other, no? Each of them is a function which can call the other function, right? And it can go to the base case, right? Yeah? If you think about it, if you find programming easier to think about, then this is what it is. Yeah? At least now that you see the grammar, does it make sense? Yeah? If you have been, yeah? Okay, good. Okay, what about this? I want to understand this language also. All nested, properly nested parentheses. Okay? It's almost like, how do we even talk about properly nested parentheses? We know what it means, right, intuitively, right? What does it mean? So in almost to specify this, I claim that we mathematically think of it really as a grammar, right? Okay, so let's understand what is a properly nested string of parentheses. What does it mean? What should we think about it as? I mean, we intuit it, right? But what is it mathematically? What does a string which is properly nested look like? Yeah. Yeah, so that's a grammar, but I'm saying, when you think of the language of the string, language of the, what does it mean that a set of, W is a properly nested string of parentheses? What do we think about it, right? We think about it recursively, right? Because it can be very big, no? So at the top level, how should it look like? It could be something enclosed with left and right parentheses, which is already a valid nested parenthesis, right? Or at the top level, how can it look like? It can be a bunch of things which are stacked, right? The concatenation of many things which are already nested parentheses. Yeah? No, you can't do it, right? Because I'm allowed, that's what I'm saying, why is this not allowed? Let's see, that's what it means to understand this, right? Is this allowed in your language or not? Yeah, no, properly nested, yeah. No, this is not nested, but the meaning of so that's why English is ambiguous, right? So when we say something is a properly nested set of parentheses, okay, so maybe I shouldn't use this, right? Okay, so I don't know what is the precise way of saying it. Is a valid, right? So this is the standard usage for a string of parentheses which doesn't have okay, let me say W is doesn't have mismatched parentheses, right? How about that? Okay, maybe this is not the right word, right? So let's say the string of parentheses which is not mismatched, right? Okay. So okay. So no. So can you generate a grammar for this, right? Even this is allowed, right? Yeah. Okay. So I claim the grammar is very simple. It is S goes to epsilon S or SS. Okay. Yeah, you sort of see it. Yeah. Yeah. I mean, we can have a top level, which can be a nested parenthesis, one level, right? A top is just only something enclosing a valid string, or I can have a sequence of them concatenated, no? Yeah? Okay? Kind of getting the hang of it a little bit, yeah? So, but see, context-free languages have the power of allowing a recursion, and that's a very powerful thing, right? Okay. Okay, because they allow recursion and nice things, we can prove some properties. Okay. Now, let's discuss some simple closure properties. So that also gives us some understanding of the power and the ability to design new languages. Suppose I have two grammars G1 and G2, and they generate L1 and L2. And because we are talking about two grammars, we have to be a little careful. We'll make sure that the non-terminals of this and the non-terminals of this are different, because if we share non-terminals, we can confuse ourselves, right? If you have S in this and S in that, when you want to put them together, the S gets a little bit tough to understand, right? So for the simplicity, we'll assume that we don't use the same letters in V1 and V2, so that we can keep them separate in our head, right? Is that okay? Now I want to know if L1 and L2 are context-free languages, is L1 union L2 context-free language? Okay. Okay, so what I'm saying is, let's look at an example. We saw that this is a context-free language, we saw that this is a context-free language, right? And I want you to accept both now. What is what is the set of strings which has both? What is their union? Okay, you can say, the union is this language, and let me design a new context-free grammar because I understand this language. No, I don't want you to do that. I want you to mechanically say, if I had a grammar for this and if I had a grammar for this, I should be able to write a grammar for their union. How will you do that? Yeah? Exactly. So, I just create a new thing, which is this, and then I have rules P1 and P2, right? Okay. I take the union of the two grammars, right? Remember, they don't share any non-terminal symbols, right? Okay. And I create a new start symbol S, and I say S can go to either S1 or S2. What will this generate? If I go to S1, what will it generate? Because I have rules of P1, it will generate L1, right? Yeah? And what will the S2 generate? It will generate L2. So I can generate a string in either L1 or L2. And I can't generate anything else, right? Because my only rule for S is you have to go to S1 or S2, right? And I'm done with that rule, right? I cannot apply this S recursively. That's the only rules for S. Okay? Does it make sense? Yeah? Questions? Yeah? Do you agree that this is true, right? Yeah. Don't be shy. Yeah. Yeah. No, I don't want concatenation, right? Because I only want to accept the union, right? Okay. Now next question is are they closed under concatenation? What does it mean that if I had a context-free grammar for L1 and a context-free grammar for L2, can I accept strings which are in L1 concatenated with L2? Yeah, S goes to S1, S2, right? S goes to S1, S2, and we have P1 and P2, we add all that. Yeah? Make sense? Okay, that was easy. Okay, Now what about a clean star? S goes to S. If S goes to S, we'll get stuck in S, right? You have to have, right? How will you get out of a recursion if you don't have a base case? Okay. Well, even that is not good, no? What do we need? Epsilon solve all the problems. Mighty epsilon. Okay. Okay. Think about it. I want you to figure it out. Think carefully, right? See, if you come up with something like that, you have to say, it seems plausible, but is it right? Okay. What should we have? What are the rules? Remember, right? S1 is. Think of, I have a grammar which has S1 here, right? And I want to create a new grammar which accepts what? L star, right? Where L is the grammar of the first. This is the grammar for that. What does L star mean? Yeah, any number of concatenation of strings of in L, right? Including 0 times, which will give epsilon. Don't worry about epsilon. Well, we have to, but that's not the key. I have to allow arbitrary amount of concatenation. Okay. Yeah. Do you need the middle rule? Yes, you don't need the middle rule, right? Yeah. Okay. Here is the thing: S goes to epsilon or S1S. And okay. So what does this allow you to do? It will allow you to, if you keep on applying this rule, what do you get? I can get S1, 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 S1 any number of times, right? And then I'll go, right? And then each of those S1s will generate a string from the language, right? Okay. Yeah? Yes? T? No, but remember that, what is T here is, T is a set, not a symbol. Right, I only want to generate concatenations of strings which are already in L. No, what are the strings that are in L? The only thing I know is that they are precisely the set of strings that S1 generates, right? So if I put S goes to S1, what does it generate? It generates the language L, right? Because S goes to S1 and S1 will generate whatever, right? If I want concatenation of L with itself, I'll put S goes to S1, S1, right? Okay. Now, ideally, I should say S goes to S1, S goes to S1, S1, S goes to S1, S1, S1. That's what we want, right? Because that is an arbitrary number of concatenation. And this is going to do the recursion for us. Okay? Okay. So once we have this, can you see why that this, can you prove this? Prove that every regular language is a context-free language. Why is every regular language a context-free language? No, every regular language, anything that I can have a DFA for, I claim it can be also written as a grammar. Yeah? No, we are trying to prove the other way. We are saying regular languages are our context-free, not context-free languages are regular. Yes, you can do that, but I claim that there are many ways of thinking about regular languages. Given that I just put this slide before, what is the most natural thing that you should think about? Right? See, remember, we defined regular languages inductively as those languages which satisfy what? That they're closed under union, closed under concatenation, closed under clean star. Right? We are showing that context-free languages also satisfy those properties, and the only thing you need to verify is that the base cases. Right? Yeah? Okay. So you choose the proof. See, so remember we did the same thing with NFAs, right? How did we argue that NFAs capture regular expressions? We argued first that NFAs have this nice property that you can do union, you can do concatenation, you can do clean star, and then we said, then we're done because they easily capture regular expressions because we verify the base cases and then inductively all the stuff is going through, right? Okay, all right. So that's the nice thing about having multiple ways of thinking about a class of languages. You can use whatever is convenient to prove what you want, right? Okay, rather than look for only one way. I say, DFAs. How do I convert DFAs into grammars? That seems like a headache, right? Because DFAs look very different from grammars, right? So how can we imagine that we can convert a DFA into a grammar? That's hard. Well, this is much easier, right? Once we prove this, then we can use the definition of regular languages using the closure properties. Okay? Okay. And you have another exercise there that I will skip. So one important thing is that unlike regular languages, context-free languages are not closed under complementation. Okay? I'm not going to prove it. Okay? They're not closed under complementation. And for that reason, because they're closed under union, but they're not closed under complementation, they're not closed under intersection. Okay? If they were closed under intersection, then that doesn't make sense. Anyway, they're not closed under complementation or intersection. They're a richer class of languages, and they're not closed. That means that you can have a language which is context-free, but the complement is not context-free. Okay? So that's not possible, right? But one nice property that you can prove, which I'm not going to prove because it's not easy to prove directly, is that if L1 is a context-free language and L2 is a regular language, then their intersection is CFL. Okay? So if this is context-free, we cannot say it is CFL, but if it's regular, we can prove the intersection. This is a hard proof. Okay? Okay. And you can say, what is a simple example of a language which is not context-free? Okay? Here is a simple example of a language which is not context-free. This is just to tell you that what is not context-free, right? A to the n, B to the n, C to the n. We can do A to the n, B to the n, right? But this is not context-free. Okay? This is just for information, just to. But the proof is not obvious how to do this. Okay, it is not easy. Okay, and one important thing about context-free languages, which is again important in programming languages, is that this notion called parse trees. Okay, remember, how do we know that S derives a string? Well, we say, okay, S derives this guy, then it derives that guy, and then it derives this guy, and eventually if it derives W, then we know S derives that thing, right? A parse tree is a compact representation of the derivation instead of writing down the sequence of derivations, right? Because that's a painful thing. This is a parse tree. What does a parse tree look like? It's a tree, as the name suggests. It's a rooted tree. At the top of the root of the tree is the start symbol S. And what are the children of that? The children of that are labeled with terminals and non-terminals. So how can we do this? This is valid because this is a what? Production root, right? S goes to ASB. So that's what we used. And then this S we can expand by BSA because it is a rule. And this we can expand as SS. And this expands to S goes to BA because that's a rule, right? And S goes to epsilon. Now, what is the string generated by this parse tree? What is this thing? It is all the leaves in the order, right? A, B, B, A, epsilon, A, B. Okay? So a parse tree is a compact way of showing how we derived a string from the start symbol. Yeah? so that you can visualize it. Okay, this is a parse tree for this string, right? All right? Any questions on the parse tree? Make sense? Yeah? Okay. So in programming languages, there could be many derivations, because if you derive things, you can swap things, right? I can expand in different orders and I'll get many derivations, right? But the parse tree avoids all that choice for you, right? The parse tree gives you one way of cleanly shows you one way of right? Okay, so there is notion of this is again coming from programming languages, and it's an important notion. And let's take this grammar. S goes to S minus S, or 1, 2, or 3. Okay, so what does it generate? It generates many things, but it will generate the string 3 minus 2 minus 1, right? You see that it will generate 3 minus 2 minus 1. Okay, what is the meaning of 3 minus 2 minus 1? Sorry? Okay, now what is the meaning, right? If I write 3 minus 2 minus 1 in my computer, what should the computer think about it as? Sorry? 0, right? You're saying. Why? Okay, so computer is okay. So it depends on what the rules of the game are. Okay, so look at the parse tree for 3 minus 2 minus 1. Okay, so this is one parse tree and this is another parse tree. Okay, the two different parse trees for the same expression 3 minus 2 minus 1, right? When the computer executes this code, what should it do? Should it first subtract 2 minus 1 and then take it off? Which order should it do, right? Well, it's important because it may be that, if you do it one way, you get some round off error in one sense, and if you do it another way, you get something else, right? You can't have this non-deterministic idea of the computer should it do 3 minus 2 minus 1 or 3 minus 2 minus 1, right? It has to know, right? It can't, suddenly think, I am confused, right? Okay. So how does it know when we write this graph? Suppose we write, how can the computer tell whether we meant it this way or that way? Right? When it compiles, it shouldn't have ambiguity about interpreting this expression as this way or that way. Okay? So a grammar is said to be ambiguous if there is a string which has two different parse trees. Okay? These are two different parse trees, right? And we don't like grammars which are ambiguous in the context of, say, programming languages. Okay? Because that is not very, very useful because it can confuse the compiler, right? So we would like, ideally, to have a grammar which is not ambiguous. What does it mean? A grammar is unambiguous if for every string that is generated by the grammar, there is exactly one parse tree. So then we can say, that is the meaning of what this string is, right? That's the semantics of that expression rather than just syntax, right? So a grammar is said to be, so can we make this grammar unambiguous? And you can change this grammar and you can change it by adding a new symbol. S goes to S minus C, or 1, 2, 3, and C goes to 1, 2, 3. Okay? If you do that, it's forcing you to do what? It is forcing you to do left to right. Okay? You can verify it later, right? So you can prove that this grammar is unambiguous. Okay? Okay? So ideally, we would like to take a grammar and make it unambiguous if possible, right? Okay, but this is just background. It turns out that some languages are inherently ambiguous. What does it mean? That there are context-free languages such that there is no unambiguous grammar which generates it. Then you're stuck, right? So it just says that, in the context of programming language, we would like unambiguous grammars. But sometimes, if your language is too rich, we cannot make an unambiguous grammar. So then we say it's inherently ambiguous, right? Remember, the inherently ambiguous is about a language, not about a grammar, okay? For a language, you can have an ambiguous grammar and an unambiguous grammar, right? But the language is inherently ambiguous if there is no grammar which is unambiguous which generates it, okay? You have to distinguish whether a grammar is ambiguous versus the language is ambiguous, okay? That's why I use the inherently ambiguous, because that means that there is no grammar which is ambiguous which will generate it. Okay, and here is a simple example. We have a grammar which is inherently ambiguous, and this is one of the skills in programming languages is to be able to design. You want your syntax for programming languages to be unambiguous, but it's actually a very hard problem in the sense that if I give you a grammar and say, is this language generated by this grammar ambiguous, it's actually undecidable. Okay? It's a really hard problem. Undecidable means that there's no algorithm for this problem. Right? So what does it mean? That if you're going to design your own programming language like C or Python or whatever, you can't rely on a generic algorithm. You have to design the grammar from scratch such that it is unambiguous and prove it. Okay? You don't have a generic tool which you write a grammar and it will automatically spit out a new grammar which is unambiguous. Okay, that's too hard a problem. Okay, anyway, that's just background. Now let me tell you a little bit about proving things. Okay, so this is the grammar we started out with, right, which is for palindromes, right? S goes to epsilon, A, B, A as A, or B as B. I want to prove that this grammar generates precisely the set of palindromes over A, B. Okay, how do we prove it? Right? Okay. So what do we need to prove? We need to prove that two languages are the same, no? There's a grammar that generates something, and there's a language we have in mind. What is that language? Palindromes, right? What is the definition of palindromes? They are all strings such that they're the same as the reverse. Yeah? Okay. So to prove that this grammar generates precisely this, how do we prove it? Whenever you have two languages, you need to prove basically both directions. Right? The language generated by the grammar is in L, is a subset of L, and the L is a subset of L of G. Then they're equal, right? Okay, there is no shortcut, right, other than in very simple cases, right? This is not just because we ask you to prove. When you design a grammar for your language, if we ask for a grammar for a language, you will design something, right, by intuition, something like that. How do you do a sanity check, right? If before you write it down and submit, or in the exam or something, and say I'm done, how do you say, wait a second, I'm not completely sure. How do I check, right? You have to check this, right? You have to say at least a sanity check of, let me see, are all the strings in that I'm generating in this grammar in my language? Okay, that's good. One side is done. Are all the strings in the language are generated by grammar? Can I make sure that I can do that? They're not the same, no? Those two directions are not the same. You could have this property and not have this property, right? Or this property and not that property, right? So you want to make sure that you do this yourself, right? Okay, so I will not do it fully, but the two directions have different proofs based on induction. Okay, so what is one direction? I want to prove that everything that my grammar generates is in the language that I care about, right? In this case, I want to make sure that if S generates a string W, then what does it mean that it's in the language? W equal to the reverse of W, right? How do I prove this? See, because I'm worried about, what are all the strings that S is generating, to understand that I should do induction on the length of the derivation. Okay? It makes sense that I say, okay, look, I look at all strings which are generated in 10 steps. If I can guarantee that, all strings generated by 10 steps are in my language, good. Then I'll use induction to prove all strings of length 11 generated by my grammar are in L. Right? I keep doing it. That's the proof by induction on the length of the derivation. Okay? And how do we do that? Well, more formally, for all k greater than or equal to 1, if S can derive W in k steps, then we have to prove that W equal to W reverse. Right? And this we can do by induction, right? You can say, okay, if S derives W in one step, that's a base case, right? What can S derive in one step from this grammar? Okay, let's go back. What is a one-step derivation? What is a one-step derivation from S? A one-step derivation from S is just a production rule from S, right? Yeah. From S, there is only one. If you can't do it, so what are all the production rules for one? S goes to epsilon A B, right? Because this is not a string in the language in the terminals, right? It is a string which contains non-terminals. So that's not. We are not interested in that because we are only interested in strings of terminals that are generated by one step, and those are epsilon A or B. Are all of them palindromes? Yes. Okay, that's easy to see. Okay, so we are done with the base case. And now we assume that for all k less than n, if S can, oh, that should be a squiggly arrow, right? S, okay. S derives W in k steps, then W equal to WR, that's our inductive hypothesis. Then let's look at a W that can be derived in n steps where, n is greater than equal to, greater than 1. Now there are two cases to consider. W is a string of length n, W is a string generated by S and it is derived in n steps, right? Okay, W can either start with an A or it can start with a B, right? So we'll just do the case of A. Without loss of generality, W begins with A. It can be, you can do two cases. Then the only way the string will start with A is that the first production should be of the form S goes to ASA, and then in k minus 1 steps, sorry, not k minus 1 steps, this should be n minus 1 steps, I derive the string W, and that will be of the form AUA, and W is AUA, right? And well, the string U is derived from S in n minus 1 steps by the inductive hypothesis. U is a palindrome, okay? And then we have to argue that AUA is also a palindrome, which is easy to do, okay? Okay, it's not hard, but I'm saying, there are two steps. One direction you have to use induction on the length of the derivation, and in the other direction, you have to argue what? Every string which is a palindrome is generated by my grammar. That's a very different task, no? This direction is every string that is a palindrome should be possible to generate from my grammar, right? I want you to understand that these are two different things, right? It's not just because we are writing some inductive proof for the sake of satisfying me, right? It's really about yourself understanding, am I doing the right thing or not? Okay? The proofs are different. So here you have to do induction on the length of the string, right? That's not the only way to do it, but that's the more natural thing. You see, you're not doing the induction on the same thing in the different directions. In one, you're doing an induction on the length of the string. In the other, you're doing induction on the length of the derivation. Okay? It's more complicated, in fact, when you have more than one symbol. S goes to A, B, C, B is calling S again, You can have mutual induction. Things can get very hairy. So you have to do what's called strengthening the induction, where you simultaneously have to worry about what is S generating, what is A generating, what is B generating, and that can be quite complicated, but you can see a nice example in the notes in section 5.3.2. Okay? All right? Okay. Yeah.
Can a state of like a guaranteed expansion?
Sorry?
Can a state of like a guaranteed expansion? Like say you have a state S that goes into say AB every time.